Today we are going to learn about scaling applications with Kubernetes, best practices. We will explore effective strategies for scaling applications, including setup and management of autoscalers, monitoring, and handling traffic spikes.
Welcome to this educational video on scaling applications with Kubernetes, best practices. As applications grow and demand fluctuates, scaling becomes crucial in maintaining performance and availability. Kubernetes offers robust tools to automatically adjust the number of running instances, ensuring your applications can handle variable loads while remaining highly available. In this video, we'll dive into the different strategies for scaling applications in Kubernetes, focusing on horizontal and vertical autoscaling, cluster autoscaler integration, and much more.
Horizontal pod autoscaling, HPA, is a key feature in Kubernetes that automatically adjusts the number of pod replicas based on observed CPU utilization or other custom metrics. This ensures that your application can handle increased load without manual intervention. Setting up HPA involves installing the Kubernetes metrics server, which collects resource usage data. Once installed, you define an HPA resource specifying the target resource metric, such as CPU or memory, and the desired utilization percentage. It's crucial to test your HPA configurations under different loads to verify that scaling occurs as expected. HPA is highly flexible, allowing the use of custom metrics to better tailor scaling to your application's needs. Vertical pod autoscaling, VPA, automatically adjusts the CPU and memory requests of pods based on observed usage. This is particularly beneficial for applications with unpredictable resource requirements, ensuring they have just enough resources without over-provisioning. To configure VPA in Kubernetes, you need to install the VPA components and create a VPA object that specifies the update mode, which can be auto, recreate, or initial. Auto mode adjusts resources while the application is running, whereas recreate mode might temporarily disrupt service during scaling. It's important to note that VPA does not currently work with HPA on the same pods, so you'll need to decide which is more appropriate for your application. VPA is excellent for optimizing resource usage but requires careful consideration of its limitations and potential impacts on application uptime.
The Cluster Autoscaler is a powerful tool that automatically adjusts the size of the Kubernetes cluster by adding or removing nodes based on the resource needs of the pods. It's particularly useful when your workloads exceed the current capacity of the cluster. Integration involves deploying the Cluster Autoscaler as a deployment in your cluster, configured with the appropriate cloud provider credentials and settings. It's essential to balance the costs associated with additional nodes and the performance benefits they provide. You can configure parameters such as the scale-up delay and scale-down delay to fine-tune how quickly the cluster responds to changing demands. The Cluster Autoscaler works seamlessly with HPA and VPA, providing a comprehensive scaling solution that adjusts both pod and infrastructure levels. Effective monitoring is crucial in managing Kubernetes autoscaling. It helps ensure your scaling strategies are performing as expected and allows you to make informed adjustments. Tools such as Prometheus, Grafana, and Kubernetes Dashboard provide insights into resource usage, scaling events, and application performance. With these insights, you can adjust autoscaling parameters, such as target utilization or scaling thresholds, to better align with your application's needs. Monitoring also enables predictive scaling, where historical data is used to anticipate future demands and adjust resources proactively. By continuously monitoring and refining your scaling configurations, you can maintain optimal performance and cost efficiency.
Burst scaling is a strategy to handle sudden and unexpected increases in traffic, ensuring your application remains responsive. It's crucial for applications that experience fluctuating demand, such as online retail sites during sales. To configure burst scaling, you should set higher maximum replica counts in your HPA configuration and ensure your cluster autoscaler can quickly add nodes. It's important to balance responsiveness with stability. Aggressive scaling can lead to resource thrashing if not managed carefully. Real-world examples of burst scaling include e-commerce platforms during Black Friday or streaming services during major events. By preparing for sudden spikes, you can maintain service quality even under extreme conditions. Custom metrics provide more granular control over autoscaling by allowing you to define scaling criteria beyond default CPU and memory usage. This is particularly useful for applications with unique performance indicators, such as request latency or queue length. To create custom metrics, you can use tools like Prometheus to collect and expose these metrics, and integrate them with the Kubernetes Custom Metrics API. Once defined, you can configure your HPA to use these custom metrics for scaling decisions. Testing and validating your custom metrics is crucial to ensure they accurately reflect your application's needs and result in effective scaling. By leveraging custom metrics, you can tailor your autoscaling strategies to better meet your specific operational requirements. Exploring real-world case studies provides valuable insights into the practical application of Kubernetes scaling strategies. We'll look at a few success stories where organizations effectively managed scaling challenges. For instance, a streaming service that handled a massive increase in concurrent users during a global event by implementing strategic HPA and cluster autoscaler configurations. Another example is an e-commerce platform that utilized burst scaling to maintain performance during a high-traffic sales event. These stories highlight common challenges, such as managing resource costs and ensuring application stability, and the innovative solutions devised to overcome them. The lessons learned from these experiences can guide your own scaling strategies, emphasizing the importance of thorough testing, monitoring, and continuous optimization. Successful scaling often leads to improved business outcomes, such as increased revenue and customer satisfaction, underscoring its critical role in modern application management. In conclusion, scaling applications with Kubernetes is essential for maintaining performance and availability in dynamic environments. By implementing strategies like horizontal and vertical pod autoscaling, integrating cluster autoscaler, and leveraging custom metrics, you can effectively manage application load and resource utilization. Continuous monitoring and optimization ensure that your scaling solutions remain effective over time. As we look to the future, Kubernetes scaling will continue to evolve, offering even more advanced tools and techniques to meet the demands of modern applications. Thank you for joining us on this exploration of Kubernetes scaling best practices.